cloaking devices, beams of light vaporizing planets, instantly teleporting across the galaxy. We are taught from a young age to box these concepts up and label them as pure, untouchable fantasy. But the boundary between magic and reality is constantly shifting. At the end of the 19th century, some of the most respected authorities on Earth, including the physicist Lord Kelvin, looked at the math of their era and stated flatly that heavier-than-air flight was a physical impossibility. A few decades later, the idea of an atomic bomb was dismissed by leading experts. They knew vast energy was locked inside the atom, but they couldn't see a physical mechanism to unleash it, until physicist Leo Szilard theorized the nuclear chain reaction, moving the bomb from the realm of science fiction into cold reality. Today, we have a precise grip on the physical laws of nature. This diagram shows our current understanding of physics, spanning 43 orders of magnitude. We can trace the rules of reality all the way from the microscopic interior of a single proton out to the absolute edge of the expanding universe. Theoretical physicist Michio Kaku uses this data to filter science fiction into 3 distinct categories. We can discard Class 3, ideas that explicitly break the laws of physics. We set aside Class 2, which involves technologies taking millions of years to build. That leaves us with exactly Class 1. These are technologies that do not violate any known laws of nature. The math is sound. The only thing standing between us and these magical devices is time and human engineering. Take the invisibility cloak. To build one, we have to stop treating invisibility as a superpower and start treating it as a standard problem in electromagnetism. The physicist James Clerk Maxwell proved that the light we see is simply an electromagnetic wave interacting with atoms. This animation shows the index of refraction in action. When a light wave hits a dense material like glass or water, it physically slows down and bends. This is why a straw looks broken in a glass of water. The material dictates the path of the light. To achieve invisibility, we need a substance with a negative index of refraction, a material that forces light to do the exact opposite of what it naturally wants to do. If we can control that index, we can force the light waves to route completely around an object and stitch themselves back together on the other side, leaving no shadow. We call these metamaterials, and they already exist in the laboratory for microwave radiation. The hurdle for visible light is purely a manufacturing one. To bend a light we can actually see, we have to build internal structures that are smaller than the wavelength of visible light itself, which requires manipulating matter at the atomic scale. Harry Potter's cloak isn't an optical paradox, it is strictly an exercise in nanoscale manufacturing. If we shift from manipulating light to weaponizing it, we run into a different kind of barrier. There's no physical law limiting the raw energy you can concentrate into a single laser beam. But building a handheld phaser requires a perfectly stable, highly concentrated portable power pack. If you try to pump the energy of a commercial power station through a handheld crystal, the material will overheat and shatter. The weapon destroys itself before it fires. Scaling that up to a space station that can incinerate a planet changes the equation entirely. You are no longer building a simple laser. To generate that kind of destructive force, you need the power source of an actual star, nuclear fusion. We are currently trying to master this on Earth. This diagram illustrates a magnetic confinement reactor. It uses heavy magnetic fields to squeeze superheated hydrogen gas, but the pressure is incredibly difficult to maintain evenly. The gas ends up bulging out and leaking, killing the fusion reaction. Nature, however, has already solved this. When a massive star dying and collapses, it can become a gamma-ray burster. The collapsing mass violently expels 2 concentrated jets of radiation with enough power to scorch a planet light-years away. Our inability to weaponize light on a sci-fi scale is dictated entirely by our current inability to harness, store, and accurately direct stellar-level energy. To figure out teleportation, we have to leave the predictable, rigid rules of classical physics behind. In Isaac Newton's world, a solid object cannot instantly disappear from one room and materialize in another. But zoom down to the atomic level, and Newton's laws collapse. Physicists like Werner Heisenberg showed us that in the quantum realm, particles don't have fixed permanent locations. Instead, they exist as smeared-out weaves of probability. This allows for quantum entanglement. Two distant atoms can become linked by an invisible tether. Their properties sync up perfectly, meaning that anything you do to one particle instantly and automatically affects the other, regardless of the physical distance between them. That connection is what allows for teleportation. By introducing a third atom and scanning it against the first, you can extract its exact information. That specific data transfers instantly across the tether to the distant particle, recreating the original perfectly, while the source atom is wiped completely blank. Scientists in laboratories have already successfully teleported the exact quantum states of photons and complex cesium atoms across vast distances. The barrier stopping us from beaming a human across the globe is the sheer scale of the math. A living person contains trillions upon trillions of atoms. Keeping all of those atoms perfectly synced up, a state called quantum coherence, long enough to extract and send the data, is far beyond our current computers. Because the laws of quantum mechanics explicitly allow for it, human teleportation has been downgraded from a magical fantasy to an incredibly brutal problem of extreme data processing and molecular stability. Whether we are talking about manipulating light for invisibility, containing the power of a star for weapons, or entangling atoms to beam matter across space, the underlying truth is exactly the same. Theoretical physics grants us permission to build all of them. We are sitting across what Michio Kaku calls the engineering gap. The only difference between our current reality and a civilization capable of exploring the stars is time and the eventual mastery of manufacturing at the atomic level. Investigating these wild ideas is exactly how major breakthroughs happen. Pushing the boundaries of what seems ridiculous is what forces scientists to uncover entirely new fields of study, like thermodynamics and quantum mechanics. Casually dismissing an idea as pure fiction just because we can't build it today is a historical trap. It is a failure of imagination that has embarrassed the leading experts of almost every century. We aren't locked out of the future. We are simply the primitive civilization standing at the threshold, tasked with doing the heavy lifting to turn yesterday's magical fiction into tomorrow's scientific appliance.